joining us live, then welcome. If you are watching this as a recording, then you're also welcome, and I hope you enjoy the content we're going to present. So this is a tutorial on Timeloop and Accelergy. They are two tools that have been developed as a result of collaboration between MIT and NVIDIA. My name is Angshuman Parashar. I work at NVIDIA. And I'm joined today by Nellie Wu from MIT, Tsai from NVIDIA, Vivienne Z from MIT, and Joel Emer from both NVIDIA and MIT. This is part 2 of the tutorial. Part 1 was posted on the website as a video, and that covers the technical background behind the tools. Today is much more of a hands-on session in which we walk through some specific exercises and hopefully get some questions. Okay, so before we begin, these are the main resources for the tutorial. There's a website on the tutorial, which you should have seen linked on the main ISPASS website as well. And that website covers all of the instructions you need to install the infrastructure for the tutorial today. This includes Docker. If you're able to install Docker, then that's the most easy and streamlined way to run the exercises. But if you do not have Docker, then there are instructions for installing them natively on an Ubuntu system as well. As we move forward, the first few slides, you're going to see on the top of the slide, you're going to see some the same link posted here that'll show you where to go to download the infrastructure. Okay, so we begin with a recap, very short recap of the technical content in case you haven't seen the technical background video, or if you're just trying to get a refresher. This is a very quick recap on what problem these tools are trying to solve. Fundamentally, what we're trying to do is map some specific kinds of workloads onto architectures and try to evaluate their performance on the architecture. And to a first order, reuse is a big component of how those workloads behave on that architecture and how efficiently they execute on that architecture. And an example of the kinds of workloads that we're interested in is this 7-dimensional convolutional neural network layer that I'm sure most of the audience is familiar with. And this layer exhibits a variety of forms of reuse. There's convolutional reuse, which happens when you slide a filter across a plane. There's input activation reuse, when you apply this multiple filters onto the same input activation. There's output activation reuse, when you accumulate partial sums over multiple channels. And finally, there's batch reuse, when you reapply the same filters to a sequence of inputs. So these are forms of what we call algorithmic reuse. But then what happens is, this is a complex network layer with a variety of multidimensional tensors. But eventually we map this down onto a 2-dimensional hardware array. And so all of these forms of algorithmic reuse need to be mapped onto forms of hardware reuse. And what are forms of hardware reuse? They are your typical temporal reuse, when you fetch a subset of your workload's data into a more efficient buffer that's closer to the data path, and you access that buffer more frequently. There's multicast reuse, when a single element that you fetch from an expensive storage is multicast onto a number of clients, a number of users of that value. And so you avoid accessing that expensive storage multiple times. And then there's network forwarding reuse, in which somebody who's used a value in a particular instance of time can forward it on to a neighbor that's connected to it in the next instance of time, instead of reading it from an expensive storage unit. Now, the interesting thing is there's a number of ways to map these algorithmic reuse forms onto the hardware reuse forms. And flexible architectures, which tends to be the kind of architectures that people are building these days, they may allow millions of alternative mappings of the same workload. And so what that means is, in order to get a fair evaluation of a workload on an architecture, it used to be that you just needed a performance model. You just, you ran the workload on the model of the new hardware that you're trying to build. That's not sufficient for these workloads, because you have to bring these mappings into the equation as well. And that's why we've built these tools, Timeloop and Accelergy. The entire pipeline is broken into two main segments. You've got the mapper segment and you've got the model segment. The job of the model segment is to evaluate a particular mapping of the workload on an architecture. And the job of the mapper segment is to find out all of the different mappings that are legal for that workload on that architecture, and explore that space of mappings in some way and tell you what an optimal mapping is. And that optimal mapping is the one that needs to be evaluated on the hardware to give you an accurate estimate of what the workload would behave like on that hardware. And so so Accelergy is a component of the model section, and Nellie will be talking about that later on in the latter half of the presentation. So the job of the model is to model a variety of DNA accelerators, and the job of the mapper is to target every architecture that's supported by the model. Okay, so if you're interested in more depth, again, I'd like to refer you back to the technical background video. Please please feel free to visit that, go through that, as well as through some of the other resources that are linked on the website. But today, what we're going to do is do some hands-on exercises with Timeloop. And to begin with, we're going to just look at the model. And what I mean by that is we're going to ignore the mapper part of it, and we're going to directly invoke the model. And to invoke the model, we need to provide it three sets of inputs. We need to give it the problem, and an example of a problem is a convolutional layer. We need to give it an architecture, of course, which is the architecture you're trying to model. And we need to give it a mapping. Remember, we're not running the mapper, so we have to tell the model how to schedule, how to partition the space of computations, how to schedule the movement of data, et cetera, et cetera. All that is part of the mapping. Given all of these three inputs, the model is going to produce a performance and energy projection. So we begin with a very, very simple problem, which is a 1D convolution. And the 1D convolution may be represented as a loop nest, which looks something like this. You go over a set of R weights, filter weights, and a set of P output activations. And in the body of the loop, you're doing this, you're scaling each input with a particular weight in a sliding window fashion. Excuse me. So to represent this in Timeloop, you would actually think about it a little bit more abstractly. And the abstraction is, the first thing you should think of is an operation space, which essentially is the number of instances of the body of this loop nest, right? How many multiply, accumulate operations are going to be there? That's the operation space, and we're basically going through an R times P operation space. That's the number of multiplies we will perform in this whole workload, and that's represented by this yellow rectangle over here. And then these operation spaces project onto what we call data spaces, or you may think of them as tensors. And these tensors, because of this projection, they're going to have a different dimensionality than the operation space. In this 1D convolution example, they all have a single dimension. right? So you've got a single slice of weights, inputs, and outputs. So you think about this, and then you represent it in time loop in this way. And so it starts with, so by the way, all of the time loop representations are in YAML format, and so this is also in YAML. And you represent the problem shape using these YAML keys. And then when we get to dimensions, that's the bulk of the representation. So to begin with, you set up these two dimensions, R and P, and they represent this yellow rectangle. It's the operation space, the dimensions of the operation space. Now, actually, something to think about is that we naturally like to think of things in terms of this loop nest, but as far as the problem spec is concerned, this loop nest is actually overspecified. It's actually describing an ordering between R and P, and that P should be in the inner level, R should be in the outer level. When in reality, that's not the case. That you may have a specific mapping that looks like this, but in general, the operation space is just, there's no ordering between them. And so these are the dimensions. And then you set up the different data spaces, which in this case are weights, inputs, and outputs. And then in this projection key, you're trying to set up these projections, which are effectively the indexing expressions over here. And so there's one entry, there's one line in this YAML list for weights, because your weights just have one dimension. There's just one array index over here. And later on, when we get to more complex examples, you'll see more lines over here because they'll represent more of these dimensions. Weights and outputs are relatively straightforward, but inputs are a little bit, they're slightly complicated because you have an addition over here. And the way time loop understands this is it's an SOP form. You can describe the projection in a sum of products form. And right now there's no product. You're not saying anything times P. You're not saying anything times R. It's just P and R. And that's why these elements in the list are single elements, right? You don't have any other elements in the list. If you did, if you did have other elements, they would be multiplied together. But then P and R are terms in this larger list, which will be added together, right? So there's an innermost list which multiplies terms together, and then you add those terms in this list, and then you have a third list, which is not shown in this example, which are multiple dimensions of the tensor. For the output tensor, we also have this read-write flag that we set to true. And that together, together this represents the entire what we call problem shape. And so all 1D convolutions will be covered by this problem shape. And then a problem instance is a specific instance of this in which you instantiate a value of each of these dimensions, R and P in this case. And so we set R to 3 and P to 16 just in this example. Okay, so that's the problem. And the architecture in this example is a simple, what we call one level temporal architecture, which just has a single PE with a buffer and a MAC unit. And to express that, we write out this YAML, and it basically represents this hierarchy. We have a node in this tree called PE. Inside that node, we have two elements, this buffer and this MAC. The buffer has a class called SRAM, and you'll understand what these classes mean when Nellie talks about Accelergy later on. And then you've got these attributes which describe, oh, this buffer has 64 entries, the number of instances, we'll get to instances later, the word width, etc. And the attributes are specific to the class. So for example, the MAC, of course, is a completely different class from the buffer. And so it has, well, a word width is shared, but it may have a variety of other attributes that the buffer doesn't understand. Okay, so that's the architecture. And remember, I said we need a third thing, we need to give it a mapping. And in this case, remember how I said that in the problem spec, we don't want to over-specify it with a particular ordering of the loops. But when we're talking about the mapping, we do want to specify that. And we do want to say, okay, and this is an example. Here we're saying, go through R in the innermost loop and P in the outermost loop. And so to represent this in time loop, again, it's a YAML spec where you would write your target is the buffer. And so you're basically It's just a convention where if you're trying to describe a loop nest that represents data movement between two levels, you attach it to a target that's the outer level. Okay, and so the target is the buffer. This is the temporal type. We'll talk about other types later. And the factors r equals 3 and p equals 16 describe these loop bounds. And the permutation rp, it goes innermost to outermost. And what that's describing is the inner loop and then the outer loop. Okay, so given these three, you should be able to run time loop on these sets of inputs. So I'm going to share my live window real quick and show you what that looks like. Okay, thank you. So these three files, the YAMLs, the one-level.arch.yaml, conv1d.yaml, and conv1level.map.yaml represent the architecture, problem, and mapping respectively. And by the way, all of these examples are in the Timeloop Accelergy exercises repository that you should have gotten access to if you looked at the instructions for the tutorial. And so what what you'll see is that I'm sorry, it's organized into. Hold on one second. Always tricky scrolling. Yeah, we're here. Each of these directories in the exercise repo has an arch, map, and prob subdirectory. And so to run time loop, what you would do is, remember we're running time loop model here and not time loop mapper. So you would say arch and this particular one level.yaml, prob, and the convolution prob.yaml, and map, and this mapping.yaml. Press enter, and it gives you some logging data. And then in the end, you see the short line on standard output, which tells you the overall utilization, which is basically a proxy for performance, and PJ per Mac, which is energy efficiency observed by this workload. Now, that's just a short form output. In reality, if you do an ls, you'll see that it emits a variety of other logs, statistics, etc. We're going to look at two specific outputs in this example. The map is interesting because what the map does is it's basically a human readable representation of the same mapping that you wrote in the YAML format before. Okay, and so this is kind of perhaps not very useful when you're using the model, but when you're using the mapper and you do not write the mapping in by hand, this map is extremely useful because it tells you what the optimal mapping is, and you can look at it in this human readable representation. The other thing that you'll see is that next to this line called buffer, it also shows you the tile occupancy, the tile size at for each of the tensors at this level. Okay, and then the next input, the next output that's useful for us is this file called stats.txt, and this is separated into two main sections. Notice this line here that says buffer and arithmetic levels. So this shows you the statistics of the buffer and arithmetic levels. And then if you scroll down, there's a section called networks, and that shows you the statistics of the networks. In these examples, we're actually not using we're not using any network energy. It's just that the energy plugin we're using is very simple. And so a bunch of these stats are zero. Okay, so the buffer and arithmetic levels have a level corresponding to each arithmetic and storage unit in your hardware. So you've got the Mac level here and buffer level here, which were the only two levels in this architecture spec. And then you have the specs that you gave as a user. And then later on, you've got all of the statistics that were emitted as a result of this execution. The statistics are also, a number of statistics are also broken down by data space or tensor. And so you can see how many accesses you had to each of the tensors at each of the levels, etc. Okay, so I recommend you to actually walk through the detailed instructions on the repository, on the tutorial repository, because there's some interesting observations there. But for today, I'll actually skip over that. Okay, let's get back to the presentation. Okay, we already walked through this. We don't need to do this again. But let's move on to the next more complicated exercise. So here, what we're going to do is add some add another level to the architectures hierarchy. And so we already had a PE in the prior exercise with a buffer and a MAC unit. We're now going to add a main memory level, and we're going to encapsulate it in a module called system. And to represent that, it's very similar to the previous example. We just added one more level. And so we added one more, you've got a subtree here and then a subtree underneath it. This section looks like the previous example. This is what we added. And notice that this is a new class called DRAM, and we added a set of, we added an attribute for the DRAM. Now, the problem for this exercise is the same. It's still going to be 1D conf, but the mapping becomes more interesting because of the added level in the architecture. So because you have the buffer level, you now have some choices in terms of how you fragment and schedule the fetching of operations into the architecture. And so I'm showing in this loop nest one such mapping, and this is a weight stationary mapping, okay? And the reason it is weight stationary is because if you look at this loop nest, the innermost loop in this loop nest marches over P, and P is an output tensor dimension. So as it changes, it's going to change the input you're referring to, and it's going to change the output you're referring to, but it's not going to change the weight you're referring to, hence the term weight stationary. And the outside of the buffer level, you're changing the, you've got a loop that iterates over weights, and that's what changes weights. But at the buffer, the weight is stationary. A single weight is going to be fetched in and held stationary over there. You'll also notice some grayed out loops over here. So I've got a grayed out loop for R0 going from 0 to 1, for P0 going from 0 to 1. By the way, we always use inclusive start, exclusive end for our loop nests. It's just a convention. And so what that means is this is really going over P1 equals 0 to 0. And so what that means is these loops are kind of, they don't need to exist. They're trivial loops. But we always include them. We call this the canonical mapping representation. And so at each level of this hierarchy, we have one loop corresponding to each dimension. And remember, we just had two dimensions in this problem, R and P. And so we have an R and P over here. We have an R and P over here. If we had more levels in the architecture, we'd have more R and P levels over there. So with this mapping, this is a complete spec of how the operations need to be scheduled on this architecture. And so given this, Timeloop should be able to produce a specific performance and energy projection. Now, in terms of energy, what this table tries to show is, if we just think about it in our heads, what are the expected values? What are the expected values that we expect the buffer to keep? How many weights, how many inputs, how many outputs? And remember, we said this was weight stationary, and so we expect the buffer to keep one weight, but we expect the buffer to keep a sliding window of P active inputs at one time, and P active out and P active outputs, which is basically all of the outputs in this example. And then it shows the number of main memory accesses you expect, and the number of buffer accesses that you expect. And so to represent this mapping, it's very similar to the previous example, but we added another mapping descriptor. So you've got a descriptor for your main memory, you've got a descriptor for your buffer. They're still temporal, and you just set up the factors. So R equals 3 and P equals 1 corresponds to the loop bounds over here. And R equals 1 and P equals 16 correspond to the loop bounds over here. And the permutation in this case doesn't really matter because there's only one loop in each block. But in general, it's inner to outer again, and it's local to this block. Okay, so this is wait stationary. And then if we wanted to do an output stationary loop, in this loop nest, we just flipped the R, the R and P loops, right? So we were going over R here and P in the outer. And again, in the time loop mapping spec, you sort of flip those and you set up the parameters in this way, and it represents this mapping. And you can reason about this table yourself and see whether whether time loops output matches up with your intuition. But we're going to do something interesting, and so for that, let's move to the live session. Okay, so over here we've got the architecture specification, the problem specification, which is the same as before, and the two wait stationary mapping and the output stationary mapping. Okay, so let's run the, yeah, this is always going to be a problem, isn't it? What I'll do is I'll just close these guys so that they don't bother us again. Found it. Okay. So let's run time loop model arc prob map. Let's run wait stationary and see what the answer is. Okay, we've got 7.4 picojoules per Mac, and let's run output stationary. Huh, it's the same energy efficiency. It didn't change. Why is that? Well, it's because you just have a single buffer level, and that buffer level is your innermost buffer level, which means all of your accesses are going to go to that buffer level. And so it doesn't, and that number of accesses is the number of multiplies, because all your operands come from that buffer level. And so it doesn't matter what you do, you're going to access that level the same number of times. And because we size the buffer to be large enough to fit the tile, whether you're doing output stationary or wait stationary, you always have what we call the algorithmic minimum number of accesses to DRAM. And so you've got the same number of accesses going to DRAM, you've got the same number of accesses going to your buffer, no matter what data flow you pick. So it doesn't matter, the energy efficiency is the same. But what if we increase the problem size to something large? Let's make it 1920, which is like a row in a 1080p image. Okay, what happens if we do this? Let's try to run the output stationary mapping. Oh, it's an error. So what does time loop say? The product of all factors of dimension P is 16, which is not equal to the dimension size of the workload, which is 1920. And the reason why that happened is because we changed the workload size, but we did not change the mapping. Can't have that. So we have to change the mapping and make it, oh, sorry, this is wait stationary. We got to change the output stationary. That's what we're toying with now. So let's make P equals 1920. Okay. And now let's go back here and try to rerun that. Aha, okay. So the PJ per, it's now a legal mapping, and the PJ per Mac actually reduced. And the reason it reduced is because you're getting even more reuse out of that output that you were holding stationary. So let's move on to the wait stationary now. Oh, we'll have to fix the P, otherwise time loop is going to yell at us again. Okay, so let's run wait stationary here. Huh, Now we get a different error. It says couldn't map buffer, map tile size of 3841 exceeds the buffer capacity of 64. Okay, so look what happened here. We created a mapping at the buffer level with a P of 1920. The buffer isn't large enough to support that. This wasn't a problem with the output stationary because we didn't change any of the factors at the buffer level. We only changed it at the DRAM level. But over here, we're changing it at the buffer level, and that's a problem. And so what can we do? Well, we can tile things, but let's not talk about tiling yet. We're going to talk about that later. But what happens if we increase the architectural buffer size to make it large enough to fit this? So it needed 3841. And the reason it's 3841 and not 1920 is because, remember, you needed to fit 1920 output activations, you needed to fit 1920 input activations, and one weight, right? So it's 1 plus 1920 plus 1920. So let's just make it a round figure of 4096 and see what happens. Hopefully, Timeloop will be able to map it now. Yes, the mapping succeeds, but now it's a ridiculously high PJ per Mac. Look at the numbers we were seeing before, 7.4, 5.7, and 197.372. So one of the reasons for that is that, look at the class for this, it's a register file class. 4096 is a really large value for a register file. And A, it's probably not a good idea to build a register file that large. You probably want to move into SRAM. And B, the models also start breaking down when you start building these large files. So we want to pick a class that's more appropriate for the size that we're building. So let's call it SRAM. Okay. So we didn't change any of the sizes. We didn't change anything. But we just changed the class. Now let's rerun the model. And now we get a much more reasonable energy efficiency. It's 15.453. It's still much larger than what we got for output stationary, which is 5.718. Okay, it's still a lot larger, but it's not this crazy number. So that's what we see from this exercise, is interesting interplay between mappings and the kinds of things that you can express in mappings or data flows and architectures. And the two sort of are interdependent on each other. We created a mapping that didn't fit on the architecture, we resized the architecture, and then we saw, okay, we picked a different class for the architecture, and so we picked the correct class, and that changed everything. So there's all of these interesting interplay of parameters that these tools allow you to explore. Okay, let's move back into I'm gonna close this up. And let's move back into the presentation. Now, for the third exercise, what we're going to do is we're going to make the problem more interesting by introducing an additional dimension, which in this case is the K dimension. So the K dimension is just a set of output channels. And so that increases the size of your weight tensor and your output tensor, but it doesn't change the size of your input tensor. But you can see that your indexing expressions have not changed for your outputs and weights. And so similar to the other problem shape, you think about this, think about the operation space, the data spaces, and the projections, and then you write this. What changed? We introduced the additional K dimension over here. And now remember when we were talking about the first example, the weight tensor had one line here for, one line here for each dimension in the indexing expression. So K and P, we've got, that's why we've got two lines here, and everything else basically remains the same. Your weights now have two, outputs now have two, inputs have exactly one. But it's this SOP form representing this P plus R expression. And when we set up the instance, we now have to give it a value for the K dimension as well. Okay. Now for our mappings in this example, we're going to try tiling. And so there's an untiled mapping as an example, and also a tiled mapping as an example. In the untiled mapping, you don't see a repeat of the same dimension in the two blocks, right? Remember, we're still moving with the same architecture, and so we still have two blocks. We've got the main memory block, the buffer in the middle, and then the buffer to Mac block over here. And so what we've done in the untitled version is mapped all of the R's to this level and all of the P's and K's to this level. No good reason why. There's no specific intuition behind why we did that. It's just an example. But in the K-tiled version, what we've done is we've fragmented K, and K was 32 in this example. And so we go from K equals 0 to 16 over here and 0 to 2 over here. And again, no specific reason. We just chose 2 times 16. Okay. And to represent that in time loop, again, it's the same old story. Corresponding to each of the blocks in this loop nest, you've got a block of YAML that tells what the factors are and what the permutations are. Okay. And again, you've got these grade loops, which represent these trivial loops going from 0 to 1. Okay. And the tiled version has this interesting thing now. You've got a non-unit K at both of these levels.
Excuse me, Anshu?
Yeah.
There's a question regarding the Lex example. Maybe you want to open the question Q&A for
I'm looking at it. Okay. That showed how you could use the tool. Implement why the outer loops with R0 and P0 were needed. This is example 1, I assume. So the trivial loops are just it's just that we have this canonical. I'm sorry, I'm jumping all about. Yeah. So we've just been using this canonical representation, and so we kind of we can always make them optional, so that any factor that you don't specify is automatically assumed to be 1. The reason we did that is because we wanted to avoid errors, especially as you're working with both the mapper and the model. As we go to the mapper later on, you'll see that mapper, when you're describing something for the mapper, you can leave a lot of things unspecified. And sometimes you get into it's easy to make errors when you try to port something that you've written for the mapper into the model and you leave something unspecified. And we just wanted to make it very, very explicit for the user. But it's good feedback. If we see sufficient interest, we can make it an option where anything left unspecified is assumed to be 1. That's not a huge deal. Okay, so let's move on to okay. So once again, please look through the instructions in the exercises repository. But one thing I want to mention is both of these, actually, let's go back to this slide. Both the tiled and the untiled variants are actually output stationary, right? They're not, and that's because you've got an R in the innermost loop at in both of these examples. And so the word output stationary is not a complete specification of what a mapping looks like. You need to describe a lot more things. It is a convenient and intuitive descriptor that sort of tells you where things are, but it's not a complete spec. And just to drive that point home even further, for the simple example with 1D convolution plus output channels and that 2-level architecture, we've got all of these variants of output stationary loop nests. In the interest of time, I'm not going to go through each and every variant. These slides will be posted on the website, and you can pause this video and look at them again. But I will point out that the innermost loop in all of these is still R, and so they're all output stationary. But the other loops are different, and some of these are tiled, some of these are not tiled. And as a result of all of those choices, you have a lot of variance in the number of main memory accesses, in the buffer occupancy, and so the size, the optimal sizing of the buffer, and that changes all of your energy efficiency trade-offs. So let's move on to exercise 3, in which we are going to go through a more complicated architecture, and this is a 3-level temporal architecture. So we added a global buffer level in addition to the register file. However, it's not particularly interesting to just keep adding levels, so we're going to do something more, even more interesting here. We're going to add bypassing. Okay, and the idea behind bypassing is that just because you have storage level, a multitude of storage levels, it doesn't mean that you need to store every tensor at every level. So here's an example in which I've said, you know what, I'm only going to store outputs of the register file. I'm going to store both weights and inputs at the global buffer, but not outputs. And I'm going to store everything in main memory because that's the backing store. Okay, and the rationale for doing something like that is if you don't store outputs in the global buffer, that opens up the global buffer's capacity for more weights and inputs. That means you can have a larger weight and input tile. Right? You only store outputs at the register file, but not weights and inputs. That means you can have a larger output tile. And that may be more optimal, right? Because sometimes you don't get reuse for all of the tensors all the time. And so if you're not getting reuse for a particular tensor, instead of just using the register file or one of these intermediate buffers as a FIFO storage or very low reuse storage, it may make sense to just bypass them. And later on, we'll see how we can ask the mapper to do that, make those decisions for us. But right now, because we're invoking the model manually, what we're going to do is in the mapping specification, we are going to explicitly say whether we want to bypass something or not. And so at the global buffer, what we're saying, we're adding this additional mapping directive, and we're saying that we want to keep weights and inputs, but we want to bypass outputs. At the register file, we keep outputs, but we want to bypass weights and inputs. Okay, and yeah, as I mentioned before, it avoids the energy cost of reading and writing intermediate buffers if you bypass it. But in return, you may get additional accesses to outer buffers because you lose the filtering effect of that intermediate buffer. And so there's an interesting interplay here. It exposes an interesting trade-off space. I will point out that it does not change the energy cost of moving data over network wires because all of the data will have to come through the network wires. It's just the whether they get stored at a particular level or not. So for brevity and expressing mappings, by default, the Timeloop's evaluator, which is basically a Timeloop model, it assumes that each data type is stored at a particular level unless you override it. Now, but the mapper does not make such an assumption. Okay, so let's jump into the hands-on and go to the next level. And you can see the input spec has the same things. You've got the architecture, oh, sorry, this was exercise 2. We've already gone through this. This is the bypassing exercise. Yep. Yeah, so we've got 2 alternative mappings here. One, which is the middle window, which does not have any bypassing directives, which means everything is stored at every level. And the right window, which is going to have these bypassing directives, and it mirrors what I showed on the slide. And let's run Timeloop on both of these. So Timeloop model, arch this from. Okay. So this is the non-bypass version. Everything is held at every level, and we see a particular PJ per Mac. And let's try to bypass it. Oh, we made it worse. Remember I said it was a trade-off? So there's no guarantee that just because you bypass, you're going to get something better. In this case, we happen to make a poor decision. So a challenge exercise is, later on when we get to the mapper, we let the mapper solve this for us, right? But right now, a challenge exercise is try to work, try to experiment with different bypassing combinations and see if you can come up with something better than the 32.227, the non-bypass energy efficiency. Okay. So we're done with this. I'm going to move back to the slides. Yep, I mentioned this challenge exercise, and please feel free to do this in your spare time. Now, next, we're going to increase the complexity, right? So we're now going to talk about spatial instances. Now, of course, you're not going to build architectures like what I've been showing before. But with this picture, what we've done is we've stamped out multiple PEs, and now it's beginning to look like a real accelerator architecture build. It's still kind of abstract, but it's getting there. And so it's the same. It's similar to the previous architecture. It's just that you've got more PEs here. And in terms of the YAML that you would describe, that you would use to describe it in Timeloop, it's almost identical, except you stamp out the PEs with this array subscript notation. Okay, and this will stamp out 16 PEs. So that's the architecture. The problem is we actually use a slightly more complex problem, but we don't need to get into that. It's a simple extension of what existed before. But the mapping becomes more interesting now, because you need to describe how the work gets partitioned between the different PEs, right? Each of the PEs is going to do a subset of the computation, and so you need to find a way to describe that. Fortunately, you can actually do that using the loopness representation we've been using for regular temporal mapping so far, except we just introduced this additional directive called the spatial for. Okay, and the spatial for, because you've got this fan out between the global buffer and the PEs, you're going to have a spatial for between this global buffer level and the PE register file level. Okay, and in this specific example, I have chosen to run the spatial for over Ks, and we'll see what that happens in a moment. But the way you represent that in Timeloop is just like we were representing the temporal mappings before. We add this additional block here, which represents the spatial block of loops. But otherwise, the syntax is exactly the same as what we were using for the temporal loops. The effect of that syntax is very different, though, right? So what this will do is this is going to map k equals 16 across that spatial fan out. I'll show that to you in a moment on the next slide. But I just want to point out one more thing over here is notice the target for this loop, it's the global buffer. And by convention, a block of spatial fors representing a spatial fan out from an outer level to an inner level are described as a spatial mapping directive targeted at the outer level. So in this case, the spatial mapping goes from the global buffer into the PE register files. And that's why we say that the target for this is global buffer. It's a convention. We could have made it more explicit, but we didn't. This is nice and compact. Okay, so what does that do? What does the k equals 16 do? Well, what it says is that as you're going from the global buffer to the various PEs, chop up the k's 16 ways and distribute one slice of them to each PE. So in our example, if you remember, we had k equals 32. So if we say k equals 13 at the global buffer level, it's gonna send 2 k's to the PE, 2 k's to this PE, 2 k's to this PE, right? That's basically what k equals 16 does. Now, that's sort of the superficial thing, but underlying that, there's a lot of interesting consequences. Think about weights, input activations, and output activations. K will affect weights and K will affect output activations, right? And so both your weights and output activations will get partitioned, and each PE will get a distinct disjoint set of weights and output activations. But the inputs are the same. They're shared across all K. And so what that means is each of the PE register files is going to get a copy of the entire input set, or the temporal input tile at this level. It also means that to send that copy, the global buffer can actually multicast it to the PEs. And so that's a really, really efficient operation because you're not rereading the global buffer to fetch all of those input activations over and over again. You read it once and then multicast it on the network. And this is something that Timeloop automatically figures out and automatically models, just because it had the k equals 16 mapping spec. Okay. So in the exercises, what you'll see is, let's jump to that. What you'll see here is the architecture and the problem as before. But what we're doing here is we're showing two different mappings. One mapping, look at the spatial descriptor for each of these mappings. In this mapping, the spatial descriptor says k equals 16. And in this mapping, the spatial descriptor says c equals 16. Okay, and that has very interesting consequences as well. K equals 16, I described to you what it does on the slide. C equals 16 does something else. So which tensors are affected by C? Remember, C are input channels. Weights are affected by C, which means your weights are still going to be distributed in disjoint manner across the PEs. Your input activations are affected by C, which means now the inputs, instead of being multicast and copied, they're going to be split up into disjoint partitions and distributed to the PEs. But your output activations do not have C as a dimension. And so that means across all of these Cs, you have the same output activations. And because output activations, what you do with output activations, you hold partial sums of the PEs and you do read, modify, write operations to them. So what that means is when output activations are being fetched from the global buffer and into the PEs, or a read of a previously written partial sum, you're going to do a multicast, just like what was happening with input activations in the K mapping. But on the way back from the PE register files and into the global buffer, though those partial sums coming in are going to perform what we call a spatial reduction. And that spatial reduction is, again, an extremely efficient operation because it's done in the network. It's done in, typically done in adders over the network, provided your hardware supports it. And if your hardware didn't support that, then instead of being able to do that reduction as it's going from the PEs and into the global buffer, you would have all of the partial sums arriving from the PEs to the global buffer, and the global buffer would have to repeatedly do read, modify, writes as it's updating all of those partial sums in sequence, which has a huge performance and energy consequence. Okay, so what you'll see is these exercises, when you run k equals 16 and c equals 16, roughly they're similar. They're sort of isomorphic to each other, except c and k get flipped. But what you should see is that the C partitioned mapping is more efficient than the K partitioned mapping because it's doing the spatial reduction, and that always has a really strong benefit. I'll leave it to the attendees and the viewers to run this exercise in their spare time. And once again, please read through the README. There are several nuggets of useful information over there. Back to the PowerPoint. So one of the takeaways behind this, and I don't know if it's obvious, but specifying these complete mappings manually is beginning to get a little tedious, because for each temporal level, for each spatial level, you have to decide what are the factors that you need to give to each loopness. You have to describe what the permutation you need to give to each loopness. You have to decide whether you want to do bypassing or not, right? So one is describing a mapping is tedious. Finding out what the optimal mapping is also becoming more and more counterintuitive. And if you're trying to do some sort of an architecture space exploration, then sort of you sort of get a combinatoric explosion, because for each new architecture that you're trying to design, your space of mappings is a little bit different, right? So it's just it's an it's not a scalable problem for a human to do, which is basically why the Timeloop mapper was created. And so let's jump into the mapper section of Timeloop now. And so this is the left half of that Timeloop Accelergy picture. And now to invoke the mapper, similar to the model, we're going to give it a problem. We're going to give it an architecture. These two don't change. But of course, we're not going to give it a mapping manually. Instead, we're going to give it some mapper parameters. You'll see what these are. They basically tweak the search heuristics. And we're going to give it a set of constraints. And you'll see what the constraints mean in a second. All right. But to understand how this works, let's go back to a simpler hardware architecture, not the spatial one. Just for illustrative purposes, we're going to go back to the simple 3-level non-spatial architecture. Now recall that a mapping, we described a mapping for this architecture by specifying these 3 different blocks, 1 block for each of the levels of the hardware, and we gave it these factors and the permutations. And we also gave it a bypass. We're not showing that on this slide. What the mapper does is also something very similar. It constructs what we call a mapping template. And so it constructs a set of these boxes, but it says, yeah, I don't know what the RP and K bounds are going to be. I don't know what the permutations are, right? And what it does is it constructs what we call a map space, which is an enumeration of all of the ways in which it can fill in these red blanks, right? So what are the factors or the bounds for the loops? What are the permutations? What are the various ways it can bypass things? And that entire combinatoric space is what we call a map space. Now, what a user can do is constrain that map space. And the constraint can be for one of 2 different reasons. One reason may be that your architecture is limited. The architecture may be, for example, you may have an architecture that's baked to be output stationary, right? And people do that to simplify the state machines, to simplify the networks. You may not want extremely flexible networks. And so as an example, NVIDIA, its spatial fan out from the global buffer into the PEs, it's over the K and C dimensions. It doesn't allow spatial fan outs over other dimensions. And that leads to a much more simplified network that's very, very energy efficient. And so you may have, so that's an example of an architecture constraint. There are also what we call map space constraints. And those are more for a programmer using their intuition and saying, hey, you know what, the architecture really does support some flexibility here, but I know based on my intuition that it's really a good idea to keep P and K to 1 here, because I don't think you'll ever see a good mapping if these were non-unit, if you try to create a tile with these dimensions at the register file. So if the user has some solid intuitions there, they can do that, and that's really helpful for the mapper because it reduces the size of the combinatoric map space, and it makes the search heuristics much, much more efficient. And yep, I've sort of alluded to this. Given a map space, a constrained map space, the mapper is going to run a heuristic search over this constrained map space in an attempt to find an optimal mapping. And for each mapping that the mapper finds, it probes the model and uses it as a cost model to tell it what the cost of that mapping is. And the model will emit a variety of statistics, right? Performance, energy of various levels. From the user's point of view, you can give the mapper a set of optimization criteria. Do you want it to optimize for performance, for energy delay product, maybe performance as the first order, but if 2 mappings have the same performance, then go for the optimal energy, and so on and so forth. There's a prioritized list of metrics you can give the mapper as an optimization criteria. So in this exercise, what we provided is 3 sets of constraints. One constraint is so over-constrained that it effectively reduces to exactly 1 mapping, right? So the map space is sized 1. And so there's you'll see when you run the mapper that it terminates instantly. And in fact, this single mapping is exactly identical to the mapping that we used in exercise 3. The next exercise in one way is one in which it's fairly constrained, but we allow all bypasses, right? We allow the mapper to explore bypass options. And remember, I said I gave a challenge exercise in exercise 3 where I said try to find the optimal bypass. Where here the mapper is going to find that for you, and you can see if yours was better than the mapper or not. And then we also have another example, which is an example set of map space constraints, which is null, which is completely unconstrained, and the mapper runs an exhaustive search, and you can see if completely leaving it unconstrained allows Timeloop to find an even better mapping than the free bypass version or not. So let's see how we're doing on time. Okay, we have a couple of minutes, so I'm going to actually go into this and show something. Okay, arc, prob, and mapper constraints. So remember, one mapping was a single mapping from exercise 3. And I'm not sure if you remember, but 32.227 is basically the exact same energy efficiency that we saw when we entered the user specified mapping. Okay, now let's say, if you remember when we tried to manually create some bypass in that exercise, we ended up making it worse. But now let's see if the mapper can find something better. So we run it with the free bypass. And so the first thing I'll point out is this log. So as Timeloop executes, it'll print out the best utilization it's seen so far, the best PJ per Mac it's seen so far, and this is sort of a very, very compact representation of the mapping. When the search algorithm is done, it prints out the optimal PJ per Mac, and 29.68 is actually excellent. It's better than what we were, we made it worse, but this is definitely better than the no bypass version. And if we let it do the null, it's going to run for even longer, but we immediately see it's already seen something better. It's 28.931, right? Okay, so I see Kelly's question. So the mapper has a variety of heuristics. It's got it can do a linear search, and it can do sort of randomish, pseudo-random searches. It does perform a variety of pruning. So I don't have time to go through all of the details right now, but it understands that certain sections of the map space are redundant. So for example, if you have permutations of unit factor loops, those are redundant, and it removes them from the map space. So it does do some sorts of pruning, but they're still extremely large. Map spaces are still extremely large, and for sufficiently flexible architectures. If you've got a relatively inflexible architecture, it's not a problem. And so better search heuristics remains an active area of research. We're always interested in better search heuristics. We put in a lot of engineering tricks to make the random heuristics better and better, but they're still not as sophisticated as genetic heuristic, for example, or something more advanced that you can do. People have suggested an A-star algorithm, but we haven't had the opportunity to look at all of that. Okay, so let's get back to the presentation. Before getting into the next exercise, I do want to point out one thing. So far, when I presented the spatial hardware level, it was just spatial along one dimension, right? It was just the X dimension that was spatial. In reality, hardware topologies are usually arranged in two-dimensional grids, and with interconnection networks such as mesh networks that allow PEs to talk to each other. So to represent that in Timeloop, we use this attribute called meshx. So in this specific example, there are 12 register files. And so you can see that the register files are numbered linearly. So you say it's still 0 through 11, but then you say that meshx equals 4. And what that tells Timeloop is, okay, I'm going to have to send X along this axis and Y along this axis. And you can specify the meshx and Y for any of the levels. Your mapping also has to change, because your mapping also has to understand what gets mapped along the x-axis and what gets mapped along the y-axis. And to do that, we use this split directive in the mapping spec. And so remember that this is for a spatial mapping. So this is when you're describing how things go from the global buffer into the register file. Now remember, we had a descriptor very similar to a temporal descriptor where we describe the factors and then a permutation. What the split does is it tells you which of these are going to go to the X hardware dimension and which of these are going to go to the Y hardware dimension. So over here in this example, I've said split equals 1, which is actually talking about this position, right? The 1th position in this permutation. And so what that means is everything below that is going to map onto X, and everything above that is going to map onto the Y dimension. Okay, and whether this is a good idea or not, if you're a programmer, you're trying out, if you're writing a mapping by hand, you get to decide if it's a good idea or not. But if you leave it to the mapper will expose all possible splits as well, and it'll try to come up with an X versus Y mapping that is optimal. Okay, yeah, so so what this ends up doing is, actually in this, if you look at the factors over here, C equals 4 and K equals 3, all of the other factors are actually 1. They don't matter. They don't matter. And so what it effectively does, it maps C equals 4 to the x-axis and K equals 3 to the y-axis. Now, what if you wanted this mapping? If you wanted to say, oh, I want K equals 4 and K equals 3, right? Which is a perfectly reasonable thing to ask. The way Timeloop works today is you can't describe this, right? You can't say K equals 4, K equals 3 as part of a single mapping block, and you can't have KK as the permutation. And so what you would do with Timeloop as it exists today is use a simulation hack, which is what we call a dummy buffer. And so what you do is just cascade, instead of doing both the X amplification and the Y amplification in the same mapping block, you split it into 2 stages. And so you create this dummy buffer level with size equals 0, and you always bypass all tensors at this level. And then you do this further Y broadcast from the dummy into the register file. And what that gives you is it gives you 2 mapping blocks. One mapping block as you go from the global buffer to the dummy, in which you can do your K equals 4 mapping, but split equals 1. And then you've got this other mapping block that goes from dummy to the register files, in which you can give your K equals 3 to and split equals 0, so that everything goes into Y, right? And so we just created this artificial level in order to give us access to another block. And again, this is a simulation hack. Hopefully in future we have a refinement to the Timeloop mapping spec that sort of allows you to do this without having to resort to this workaround. Okay, so the final thing I want to mention is this notion of partition buffers. A number of architectures have these what we call partition buffers. So they're at the same level, but they're not perfectly shared. So they're sort of distinct buffer sections. You've got one section that's cordoned off for the inputs, one section that's cordoned off for the weights, p-sums, etc. And they may be implemented in different disjoint SRAM arrays. And so they're actually more efficient to access than if they were a shared SRAM array. And so the way to model that in Timeloop today is actually model that as a hierarchy, as a stack, right? You place them in a stack of input rect files, weight, and psum in this example, and then you use the bypass directives to make sure that you just keep psums here, just keep weights here, just keep inputs here. And again, this is a temporary workaround. We will support partition buffers, hard partition buffers natively in future. Of course, shared buffers are still supported, right? So if you have a single buffer and you just dynamically share it, you're good to go. Okay, so exercise 6, I won't go through this. This is a really complex exercise that that you can follow up with in after this tutorial. Please look at the directions on the website, look through all of the specification files, and run it. What this is doing is it's actually running a complete CNN layer on the Iris V1 architecture. And so you'll see that the architecture spec is far more detailed than all of the examples we've shown before. The constraint sets are far more detailed because it's trying to model the constraints that the actual hardware has. And the map space constraints also have a number of sort of tweaks to direct the mapper in certain directions. Okay, so the some final thoughts. The mapper is automatically multi-threaded. If you don't manually specify a number of threads in the mapper specifications, it will probe the host CPU, find out how many logical CPUs there are, and it will spawn that many threads. And there's a feature called live status that's extremely useful as you're running these long map space runs, because it tells you how each of the threads is doing, what the best mapping it has found so far. And if you're sort of just if you're not running a serious experiment and if you're just toying around, then you can always use Control-C to tell the mapper to stop doing what it's doing and terminate. And there's a variety of other tweaks that are mentioned on the mapper tweaks are mentioned on the tools documentation, Timeloops documentation. Okay, I'll skip through this, and because it's time to move to the second part of this talk, which is Accelergy. There are a variety of these resources that are on the tutorial website. Please look through them, and please feel free to contact us if you have any questions. Okay, thank you very much, and I'll turn things over to Nellie.
Yep, thanks, Angshu. I'll share my slides. All right, so that's enter the second part of Accelergy. And again, as Angshu has mentioned, we have these background lectures on Timeloop and Accelergy, and here I'm just going to do a simple recap of what this tool does, and I will be focusing on how we can use Accelergy. So Accelergy is aimed to help us to have a quick energy evaluation of the arbitrary potential accelerator designs in the large design space. It's not only limited to deep neural network accelerators, it can also be used for other types of accelerators. But in this exercise, we are going to mainly focus on how to use Accelergy for deep neural network accelerators together with Timeloop. And let's have a quick understanding of how we can develop the accelerator architecture. So first, we would have a architectural blueprint at the architecture stage where we specify the high-level components in the architecture. We can then, with the defined architectural blueprint, go to the RTL model, which describes the complete hardware attributes of the architecture, which can then be laid out into a physical layout and fabricated into a physical system. So during this process, what we want to do is to actually evaluate the energy efficiency of a potential design that we're looking at. And we do want to do this at an early design stage so that we don't spend all the efforts for developing the complete hardware description of your potential design and then realize it's not a good choice. So what we're focusing on is to have a architecture level energy estimator, which estimates the energy efficiency of a potential design right at the architecture stage. It takes in the architecture blueprint with the high-level components in the architecture and produce the energy estimation for this potential design. And since we have much fewer high-level components in the architecture blueprint, the simulation time on for the energy estimation is usually short, and we could further only explore the design space at this architecture stage without going to any details of the hardware description. So we can iterate through all the potential designs at the architecture stage and find the best design with the best energy efficiency. So this allows us to have a short turnaround time for each potential design in the design space. And once we have found the most energy efficient design, we can then go ahead and implement its RTL model, physical layout, and finally fabricate it into a physical system. So the tool Accelergy belongs to this architectural level energy estimation domain, and it helps us to have a quick design space exploration for the various types of accelerator designs. And comparing to the existing architectural level energy estimators, which use a fixed architecture model to represent a general purpose architecture, we are more flexible in terms of architecture description because accelerator designs usually have very different architectural compositions, and it is not easy to use a fixed template like what was used in the existing tools to model an accelerator design. So at a high level, we propose the accelerator infrastructure. It is able to perform architectural level energy estimations to enable rapid design space exploration. And since the accelerator designs are designed for different domains of applications, their architecture are very diverse. So we support the modeling of diverse architectures with various underlying technologies. And furthermore, we improve the energy estimation accuracy by allowing fine-grained classification of components' runtime behaviors. And you will see later how this is reflected in the inputs to the tools. And also, we want to support succinct modeling of the complicated architectures in the accelerator design space by allowing compound components. And we will also show how to use a compound component description to enable this feature later in the compound component section. So as a recap, this is the high-level infrastructure of Accelergy energy estimation framework. So I'll just quickly go through what are the important blocks in Accelergy. So it takes in the architecture description of a accelerator architecture. It uses a energy reference table or an area reference table generator, which queries external energy estimation plugins or area plugins to generate the energy reference table and area reference table for the components in the architecture. And the energy estimation plugins are, we provide some default ones there, but also you can add your own estimation plugins, and we have a very flexible interface for that, and we'll also show that later. So Accelergy will produce the energy reference table and area reference table. It will then take in another input, which is called action counts. Action counts describes the runtime behaviors of the components in your architecture. So for example, how many times a memory is read or written, and how many times the multiplier has been multiplying. So the action counts input together with the static ERT and ART will be combined inside Accelergy and then generate energy estimations for your architecture. So this is the general flow for the architecture for the Accelergy tool. And we have also mentioned we allow succinct description of the architecture description by allowing compound component description. So Accelergy can also take in an additional input, which is called the compound component description, that defines a complicated component in your architecture to make your architecture description much simpler. And we will show that later in our exercises as well. So let's now dive into how can we actually use the tool Accelergy. And first, let's take a look at an estimation of architectures with only primitive components, which are the building blocks of the accelerator architectures. So right now we're not looking at the complicated compound components yet. Just as a recap of how Accelergy works in a pictorial way. So a simple architecture can be modeled with primitive components. So for example, SRAMs or max units will be the primitive components that we consider in architectural world. And the first step is to generate the energy reference table. So you can see that in this example, we're taking an architecture that's very simple with a on-chip global buffer of SRAM type, and a local buffer and a MAC unit. The buffer is also an SRAM, and the MAC is just a MAC computation unit. And each of the components belong to a primitive class as shown in purple. And in order to represent the inputs, the primitive component library, and the outputs, we use the YAML format, just as Angshu just showed in the previous part in Timeloop. So what happened would be Accelergy will take in the YAML format description of the architecture. It will create the primitive component library to see what each primitive component class actually means, and create the estimation plugins to generate the energy and area reference tables, and then output the tables as YAML format as well. So let's take a look at the detailed description of the architecture, primitive component library, and the ERT and ART. So first, let's look at the primitive component library description using a YAML file. And this library is stored inside Accelergy. So what does this library describe? First, it describes a list of primitive component classes that we care. And in this example, we're showing two primitive component classes. One is a bitwise operators, and the other is the integer adders. And one important type of properties for these primitive component classes are what are the important hardware attributes for the characterization of these primitive component classes. So now you can see we're specifying this using the keyword attributes. And of course, the most important attribute would be what technology are you building this component upon. And in this case, we're using 65 nanometer. And for each primitive component class, they also have some unique properties that they care. So for example, the data width of the bitwise operator is important, and for the adders, both the data width and number of pipeline stages are important hardware attributes for defining the hardware component. So another thing that we want to know about the primitive component classes are the associated actions for these classes. So you can see the actions is basically the operations that can be performed by this class of components. And for bitwise, it's very simple, and we just call it process. And for adder, it can perform an add operation, or it could just be idle. So you can define various types of actions for your primitive component classes. And note that all of the names of the attributes and actions are user defined. So if you have your own special primitive component class, you can definitely give them arbitrary names, arbitrary attribute names, arbitrary action names as you want. And Accelergy will be able to understand what you mean. So as I have said, Accelergy comes with a set of primitive component classes by default, and these are the ones that we experimented with for deep neural network accelerator architecture designs. And if you are interested, you can take a look at the default ones, but you could also add your own primitive component classes by modifying the Accelergy config file. And I'll talk more about the config file later, but the config file basically specifies where you can find the different primitive component class specifications, and by adding your own primitive component class specification file, Accelergy will have a wider knowledge of what the available primitive component classes are. And for actions, we just show very simple actions with a name, but actually you can have fine-grained actions, which are very helpful for having a much more accurate estimation of the energy. So here recall, this is the same example that we used in the lecture. So basically what we're showing here is for a register file, we could not only just have the read and write operation, we could make it more fine-grained in terms of action classification. And now we're showing 5 different actions for this register file. And you can see that the energy difference between these fine-grained actions can be 5x different. So so this is just a simple example showing that we could have much more actions for a component, and listing all of them in a list would be very tedious if we have, for example, 100 actions for network components. So here what we support is we support a specification of arguments for these actions. And as shown here, we have repeated read and random read both belong to read. Repeated read refers to the fact that we're reading the same address with the same data out of the memory storage. So then you can see we can specify an argument for this read to represent a repeated read. So the data delta means how much does the data wire switch. And in this case, since we're reading the same data out for some consecutive cycles, the data delta will be 0. And the address delta is asking us how much does the address wire switch. And since for the repeated read case, we're still reading the same address out, it also has a 0 delta. And for random read, we could define it as have a 1 for data delta because the data is random, and have a 1 for address and because the address is random. And you can imagine that we could have a range not just from 0 to 1. We could have, for example, for a number of destinations of a network, we could have from 0 to 100. And similarly for action write, we could specify the arguments to represent all these fine-grained actions that we can classify out of the write. And in order to represent this in YAML format and make it understandable by Accelergy, what we do is very simple. So here we're showing a primitive component class register file. And again, we have the attributes of the register file. So the main focus here in this example is the action specification. So instead of listing all of the fine-grained action names, we only have 2 categories. One is the read and the other is the write. However, in order to fairly represent all these different types of read and write, we specify the arguments for the coarse-grained read and write actions by having the keyword arguments. And you can see the data delta and address delta arguments specified here. And the dot here after the data delta basically means the range. So in this example, the data delta can go from 0 to 1. And as I have mentioned, you can imagine you have a network component which can multicast to 1,000 different destinations. And in that case, if you want to fine-grain classify the different transfer behaviors, you could have an argument of number of destinations of having a range from 0 to 100. So this is a high-level introduction to what a primitive component library can look like. Let's look at the architecture description. So the architecture description describes the following behaviors or following properties of the components in architecture. First, we want to know the hierarchical relationship between the different components in your design. We want to know for each component which primitive component class it belongs to, so that we can have a better idea of what hardware behaviors you'll have. And also, we need to define this component by specifying the hardware attributes associated with this component. So let's go step by step. First, we want to have a hierarchical representation of the architecture. And on the left, I'm showing a flattened view of an architecture description. In the middle, we're actually representing the hierarchy of the architecture. And on the right, I'm showing the YAML format for reflecting such a hierarchy or such an architecture. So first, we have at the root level the design. And we have another level in the architecture, which is the PE. So you can see here in the YAML file, we use the subtree keyword to represent such hierarchical relationship, which is basically saying that in this architecture, we have 2 important levels. One is the design, the other is the PE inside the design. And the global buffer, MAC and buffer, those components are actual hardware components that can be instantiated and will be used for processing. So they are not like the hierarchies we just talked about, like the PEM design. They're abstract and they are not really hardware components. The global buffer, MAC, and buffer are actually components. So in order to distinguish those two types of components in the architecture, we use a local keyword to specify these hardware instantiations. So you can see here under the design hierarchy, we have a local component global buffer, and inside the PE, we have a local buffer and the MAC. And only these hardware instantiations will have associated component classes. So in this case, our global buffer and local buffer are of SRAM class, and MAC is a MAC class. So the keyword class specifies what primitive component class this component belongs to. And furthermore, we want to specify the hardware attributes for each component in the design. So you can see that we are adding the keyword attributes for each local components. And for the attributes that are specified under the subtree, it basically means this attribute will be shared across the lower levels in the tree. So basically, the technology attribute will be applied to all of the hierarchies or components in this tree. So now we have both the architecture description defined in YAML format and the primitive component library defined in YAML format. And we can see that we also have an important top-level key that specifies what this what the type of this file is. So in this case, for example, architecture description will have a top key architecture. And of course, primitive component lives in Accelergy, so it doesn't really matter. So with these two inputs, Accelergy will produce an energy reference table, which basically tells us what's the energy per action values for the components in the architecture. And here we're showing a high-level description of the energy reference table in YAML format. So first, all of the components are listed in a flattened fashion with component names to reflect the hierarchy. So you can see here, for example, the MAC is inside the PE and the PE is inside the design. So instead of having a tree format, we use a flattened name to better show the hierarchy and make the ERT easier to read. And as I have said, ERT, the main purpose of the ERT is to describe the energy per action values of the actions associated with each component. So you can see that inside the ERT, there is a key called actions, and under actions, we list the various types of actions associated with a component, as well as the energy consumption for the action. And if your component has an action that has arguments, Accelergy will produce all the possible combinations of the argument values and assign an energy per consumption value for all of the different possible combinations. So now we have seen this statically. Basically, Accelergy takes in this YAML architecture description. It looks at the primitive component library to understand what are the components in this architecture, creates the external energy estimation plugins, and produce this energy reference table, which tells you what's the energy consumption per action for each component in the architecture. So let's take a look at it live so that we can see how we can use it in a terminal. Let me share my... Okay, great. So let's look at the first example where we use an architecture with only primitive components and generate the ERT output. So here we have the inputs, which is very simple. It's just the architecture YAML, and that's what we do is we'll do Accelergy and give it the input folder, and it will be able to look through all the files in the input folder and produce an output. So you can see here, it has a lot of logs, basically telling people what it sees. It could tell you what primitive component class definition file it has seen or what external energy estimation plugin it has identified. And in the end, it tells you what output is produced by looking at the available inputs. And we can see here we have the area reference table, the energy reference table, a flattened version of the architecture, and as well as the summary version of the ART and ERT. So I can briefly show the ERT table, and this is just as expected. You can see that the keyword tells you what this file is for, and for each component that has a flattened version of the names, and for each action associated with the component, it provides an energy consumption for each action. And you may be curious about what the summary does. So let's take a look at the ERT summary file. It still tells you the energy consumption of the components, but it also tells you which external energy estimation plugin is used for estimating this component. So for example, in this case, you can see that the MAC component is estimated using an estimator called Aladdin table. This is a 45 nanometer energy estimation table that would provide as default plugins. And something it also does is for the actions with a lot of arguments. So you can see here the read action has many arguments as we just showed. In order to make the descriptions succinct, that has a summary of what's the average, min, and max for this specific action. So this is just to show that how Accelergy takes in the input and what does it look like for Accelergy to produce this energy reference table. Let me go back to the slides. Okay, so we have shown that the very first step of producing the energy reference table. If you recall that we also have a second step where we have the energy reference table already, which records the static energy per action for the components. And we also take in a action count, which comes from a performance model, such as a cycle accuracy simulator. And it has the information about how many times each component is accessed or operated on during a run of a specific workload. And of course, Timeloop is able to produce such action counts as you have seen in the previous section, and basically, except Timeloop, you can also use other simulators to produce such an input. So Accelergy will take in an action counts and its own produced energy reference table to produce the energy estimation for the architecture. So let's take a look at what action counts looks like. So as you can imagine, the action counts must have some agreement with the architecture description because it's describing how the components in the architecture are working during a run of the workload. So similarly, action counts also use the subtree and local keyword to specify the abstract hierarchies in the architecture and actual component instantiations in the architecture. For each actual component in the architecture, it will record how many times each action of the component has occurred. So in this example, if let's look at the global buffer case, it says this action count file is basically saying that for the read action with data delta equal 1, address delta equal 1, meaning for the case of random reads, we have 20 occasions during the run. And similarly for the writes, you can also define the number of times. And with that, for each component, we will be able to know what its runtime behavior looks like. So again, Accelergy will be looking at the YAML version of the energy reference table and look at the action counts to generate the energy estimation. So one important thing is if you are running different workloads on the same architecture, you can imagine that your ERT table will never change because you will have the same components in your architecture, no matter what workload you run. The only thing that will change will be your action counts. So if you're running different layers of a network, the number of times the components being operated on will be different for each layer. And in this case, in order to avoid generating the same ERT every time, Accelergy is able to identify that once provided with an ERT, it will not parse the architecture and correlate external energy estimation again and again for the same ERT. So it will use the ERT provided directly and combine it with the action counts to save energy estimation overhead. So we can also quickly show how that works. Okay, so let's go to the second example. And inside the input, you can see that we have the ERT. We are not looking at the architecture anymore. We have the ERT YAML, we have the action counts YAML, and with these two inputs, Accelergy will be able to produce the energy estimation. And similarly, we just give it the input folder, and it will identify what to do. And we can see that the output of this will have the energy estimation YAML here. If we look at the energy estimation YAML, it's very simple. It tells you for each component what is the energy estimation, and also it gives you a total energy estimation for the entire architecture. So that's that, and you can see that it's much faster if you already have the ERT and just change the action counts file, especially if your external energy estimation plugin takes a long time to run for the generation of the energy reference table. Okay, all right. So we have been talking about very simple architectures with primitive component class such as SRAM and Mac, but you can imagine that we could have architectures that are much more complicated, and the complication mostly come from all the control logic such as address generation or intersection unit inside your architecture. It's not that simple where we only have the SRAMs and the computation unit. So here, so that's why we introduced the concept of a compound component description. This is basically to help us succinctly model arbitrary complicated architectures with a very simple architecture description. But inside the architecture description, you could have user-defined compound component classes. So if there are a lot of details described in the background lectures, but here let's just look at it from a very high level. If you look at the architecture description, we still have the same structure where we have a global buffer, a MAC unit, and a local buffer inside the PE. But what is different is if you look at the classes, which are the purple text for each component, we can see that we have a class that you might or might not understand, and this is actually a user-defined class. And we could have user-defined class for different architectures depending how you want to implement your components. And in our specific case, we have two user-defined classes. One is a smart buffer. One is a MAC with a FIFO, which is called a MAC FIFO. It's basically a MAC with a FIFO channel. And what the compound component description does is to describe what each user-defined which is user-defined class means. So for example, for smart buffer, it is basically two address generators, which is trying to help the storage unit to generate the stream of read and write accesses, and the SRAM storage unit. So it's not only a storage unit anymore. And for the FIFO, again, we have not only the MAC, we also have a FIFO channel to send out the output to the other parts of the architecture. So if you don't have the definition of these compound component class descriptions, you will have a very clustered architecture description. However, in this way, with the architecture description and compound component description, both the architecture will look much succinct, and also the compound component description can be used across different components, and the reusability is very high also across different architectures. So Accelergy will be able to understand the architecture and understand the compound component description, and with the understanding, you'll be able to appropriately ask for the energy estimation plugins for the energy per action values for the components in the architecture. So let's look at an example of how we do this with the YAML files. So again, we have a very similar description for the architecture spec, because what we do is we only need to change the class of the components involved in this architecture. So you can see that here we're changing them into very high-level component classes, smart buffer and Mac FIFO. And we also need to define the compound component using compound component descriptions. So we want to first define compound component descriptions, hardware implementation. So how is this compound component implemented using the primitive component class? And there are two aspects of this. One is we want to have a tree level representation of the hardware implementation hierarchy. And also we want to map the hardware attributes from the compound component class to a lower level primitive component class. So let's look at how this works in our YAML specification. Again, you can look back to the lectures about how the smart buffer works in detail. Basically, what it does is it will generate a read address using the address generator, and the buffer will be accessed accordingly. So now we have an architecture with a root of a class called smart buffer, and we have two address generators, one for read and one for write, and a local and a storage, which we call it buffer. And you can see that we can use a simpler way of specifying multiple identical components in a compound component by having the dot representation. And also each of the subcomponents for this compound components needs to have a class. And in this case, we're using adders to represent the address generators. And in terms of YAML specification, you can see that we're using subcomponents keyword to specify what are the primitive components involved in this compound component classes. And we're also specifying the primitive component class associated with each subcomponent using the class keyword. And as I said, we also want to describe the hardware attributes associated with the compound component class. Again, we're using very intuitive attribute names, technology width and depth of the smart buffer, and you do want to project it to the lower subcomponents of which are primitive components, so that we can have a good way of estimating energy consumption of this high-level component. So what happens is basically for each subcomponent, we'll specify the attributes for them. And you can see that we're using attribute mapping from lower level to higher level, so that we could be easily changing the higher level attributes and have it automatically reflected for the lower level primitive subcomponents. And we also support different types of arithmetic operations for these attribute mapping, and you can find more details in our examples. And as we have seen for the primitive component classes, we need hardware attributes. We also need actions. So we also need a way to represent the actions associated with the compound component classes. And we do this in a similar fashion. Recall that the read to a smart buffer involves a address generation from the address generator. And since it's an adder, it's basically an add action. And for this read, high-level read action, we also have a read to the buffer as well. So then we are defining this compound action read as involving two sub-actions, each related to a subcomponent. So you can see here in the description, then we're specifying the actions of the smart buffer in a similar format as a primitive component class, where we'll list the name of the action, the arguments associated with the action. And what's additional here is we also want to specify what subcomponent actions are associated with this high-level compound component action. So we are still having argument mappings to the higher level actions associated with the compound action in a similar fashion as what happened to the hardware attributes. So now with this, we have the architecture, we have the smart buffers specification for the compound component, we can then generate the energy reference table and the action count for this architecture. So I'm not going into details about how the run looks like. It's very similar to the previous exercises. You can look at exercise 3, which has specifications of the architecture and compound components. And if you give all of them to Accelergy, Accelergy will be able to generate the final energy estimations. And we also have a Aries-like architecture, which, as Angshu has already mentioned in previous section, has a very complicated architecture. So as you can see here, we have a very high-level description where we have different types of global buffers, different types of networks, and different local scratch pad inside each PE. And in this example, we have a Aries architecture in the exercise 4, where the architecture is composed of various compound components, and you can try to use Accelergy to model the Aries-like architecture, which is much more complicated than what we have shown in the previous examples. The third point that I want to talk about is what can we do in terms of modeling different designs with various underlying technologies. You can see that we have different energy estimation plugins in the high-level Accelergy infrastructure figure we just showed. And how Accelergy know there are external energy estimation plugins. So the way Accelergy does it is it has this Accelergy config file, which is automatically created by the first run of Accelergy. And it is stored, I think it probably depends on your system, but it's stored in the .config folder of your system. And in here, we're specifying the paths to the energy estimation plugin. And for the default plugins, once you install the plugin, this path will be automatically updated inside the Accelergy config file, so Accelergy will be able to locate all of the installed external energy estimation plugins. And I also want to talk about, once Accelergy identifies the plugin, how does it interact with the energy estimation plugin? So it's a two-step process. First, it will send a quick check to all of the plugins it's able to identify, asking them, can you support a specific request that I have? And the request is basically, can you give me the energy consumption of a specific action for a specific component? And the plugin, the energy estimation plugin, will give a response in terms of the energy estimation accuracy for this specific request. And Accelergy will do this to all of the energy estimation plugins able to identify. And notice that at this step, the plugins are not generating the estimation yet. And the second step is, once Accelergy has asked all of the available plugins, it will determine which plugin has the best accuracy by looking at their responses. And only when it determines which plugin to ask, which is basically the plugin with the highest accuracy, it will send the actual request for the most accurate energy estimation plugin to perform the energy estimation. This saves us a lot of time if each of the plugin takes a long time to actually generate an estimation. And in this way, we only require one of the plugin to perform the estimation task. And so what if, as I have mentioned, we open source several plugins, but it's also possible that none of them support your purpose. And we also provide a way for you to have your own plugin installed into our system. The simplest way is to use our provided table-based plugin and use your own CSV table to easily plug and check for user-defined CSV tables for different components. And how this works is basically we have this provided Accelergy table-based plugin, and we already gave you a default set of CSV tables. You can provide your own CSV tables. So for example, if you are working on processing memory-based accelerators, you could provide a CSV table for energy estimations of memory star designs. And in this case, Accelergy will be able to pick up your table for the energy estimation. And of course, you could have different tables for different purposes, and Accelergy will appropriately use the corresponding table for the energy estimation of different architectures. So I guess this is a reference basically for you to check whether your table successfully gets identified by Accelergy. Inside the Accelergy config file, every time you add a table, you will see that the roots key for table-based plugins will have one more item in the list. And the command to add a new root, which is basically a command to add your table, is basically to use the command accelergy tables -r and the path to your own table. So once you run this command, you'll see your table being added into the Accelergy config file. And once it's added, you will have Accelergy being able to use your table for components in your architecture. So we actually have one such example in our exercises, which involves the processing memory architecture. And processing memory is a new technology, so you probably can't use the default tables for 45 nanometer estimations. So we need to have Accelergy identify a new table. So I'll quickly show the example here. So if you go to the processing memory exercise folder, you can see that we're providing a PIM estimation tables. And in here is basically a set of CSV tables. You can see there are memory state data and 32 nanometer data for processing memory-based architecture estimations. And what you want to do is you will do accelerate tables -r processing memory estimation tables. And you can see this path to your estimation CSV tables is now added as a new root for table-based plugin. And now if you estimate the energy consumption of a processing memory-based architecture, you can see the tables being used. I'll quickly run this. So, and then in order to see what estimation plugin is used, you can look at the summary. So very easily you can see for the scratch pads or the computes, your table-based plugins are actually used for the estimation. So this is basically saying that your CSV tables are identified by the Accelergy tool. So you can play with this later. You can change the values of the data inside tables and see whether Accelergy can pick it up. We also have other exercises and baseline designs in our different folders in our exercise Docker. You can play with all these more complicated architectures to see how the Timeloop plus Accelergy system work. It has architectures like Aries or Simba and many others. And I think this is all that we want to show for the exercise and Timeloop Accelergy part for this tutorial. And if there is any question, we could answer them.
Okay, thank you, Nellie. And we'd like to thank the attendees and also thank whoever is going to be watching this as a video later on. Once again, please let us know if you have any questions about the tools. These tools are all open source, and the resources are all provided on the tutorial website on how to get access to the infrastructure, get them running. And we hope these tools are useful for you in terms of the research that you're doing. And if you would like to contribute, once again, please let us know, and we welcome contributions. Thank you very much. I think we can end the recording.